Here in video number 3 for basic chemistry, we're looking at how you understand acid, base, and pH as it's associated with the human body. So acids and bases themselves are associated with pH, and pH is any fluid, the pH of any fluid is a direct measurement of the number of free-floating hydrogen ions and, to an extent, hydroxyl ions. We've already looked at these a little bit since we know that water in itself can ionize, producing both of these types of ions. Now keep in mind that you're going to have hydrogen ions and hydroxyl ions present in body fluids at all times, and that you never want to eliminate all of either the hydrogen or the hydroxyl ions. You just need to find the correct balance between the two. So we do, of course, register pH based on a relative concentration of hydrogen ions. You do not need to know this equation here, but one of the things that I do want you to recognize is that it's associated with moles per liter, right? And this is quantifying how many of these hydrogen ions are going to be expressed per liter. And so when you see something like the pH of 7, that means that the concentration of free-floating hydrogen ions is 10 to the negative 7 moles per liter. So of course, each time you look at a pH unit, you're either going to see it move in a tenfold increase or decrease in ion concentration. Again, this is because they're so tiny that we look at it in these tenfold amounts because of the type of effect they can have as they are dissolved in solution. So now, acids and bases are going to be those kinds of chemicals which are going to alter pH in some way. Acids are proton donors because they release free-floating hydrogens into the water. And bases are proton acceptors. So usually these are going to contain a hydroxyl group, and that negative charge on that hydroxyl group can usually bind to the free-floating hydrogen ions. So of course, you've got to imagine that it's like you're playing throw and catch with free-floating hydrogen ions. Acids are throwing these out into the solution, and bases are trying to catch them and pull them out. Again, remembering that any of those free-floating hydrogen ions that are thrown into solution by an acid and not picked up, those are going to start to affect the pH. Now, you will have a certain number of free-floating hydrogen ions at all times, and if you end up with too many bases, those bases try to catch too many free-floating hydrogen ions, also affecting the pH. So again, you want a nice balance between them. The pH scale is going to help us understand the relative number of acids and bases within a solution. And we start right here by looking at a pH of 7 that tends to be referred to as neutral, because in a situation like this, the concentration of hydrogen ions and hydroxyl ions is roughly equal. Now, as you begin to see more free-floating hydrogen ions than hydroxyl ions, you're starting to become more acidic. So this is going to be a pH that begins to drop below 7. When you look at this scale right here, you see what that looks like. So here's a pH of 7, where you have the number of free-floating hydrogen and hydroxyl ions being equal, 10 to the negative 7. You can look at some solutions right over here. Blood is around 7.4, 7.45 in pH, so it's relatively close to neutral. But as you begin to look down this list, milk, followed by black coffee, wine, lemon juice, and hydrochloric acid are becoming more and more acidic. So the question is, what's changing about these solutions that's making them more acidic? Well, the idea is that you're starting to see an increase in the number of free-floating hydrogen ions. So 10 to the negative 7 is fewer than 10 to the negative 6, which is fewer than 10 to the negative 5. And so you're building and increasing all the way to 10 naught down here in the number of free-floating hydrogen ions. At the same time this is happening, you're actually decreasing the number of free-floating hydroxyl ions. So 10 to the negative 7 gets smaller, so there's fewer of them at 10 to the negative 8, even fewer at 10 to the negative 9, until there's so few, 10 to the negative 14, concentration of free-floating hydroxyl ions. Now, whenever your pH begins to creep above a pH of 7, that's the kind of solution we refer to as basic or alkaline. So now the number of free-floating hydrogen ions is less than the free-floating hydroxyl ions. You're looking at this table right over here. You start with neutral and you run up. So in this case, the number of free-floating hydrogen ions is decreasing to negative 8, 10 to the negative 9, 10 to the negative 10 to where it's the smallest number that we can register on the pH scale. All the while, the number of free-floating hydroxyl ions is increasing, 10 to the negative 7, 10 to the negative 6, all the way up to 10 naught here. So you can see that starting back with blood, your egg whites moving to bleach, then to ammonia, then to lye, and sodium hydroxide are becoming increasingly more alkaline or less acidic. And so you need to be able to read a pH scale. You need to understand the basic concentration differences between hydrogen and hydroxyl ions, how that's associated with the pH scale numerically, and how that's referred to as either basic, acidic, or neutral. So be familiar with those relationships. Now here I've given you a list of some acids and bases, and I do want you to know those. Hydrochloric acid is going to be an acid because as it dissociates, it breaks into hydrogen and chloride ions. Those hydrogen ions are now free-floating and can alter pH. Acetic acid, also donating free-floating hydrogen ions. And carbonic acid, donating free-floating hydrogen ions. As you come over here and take a look at bases, we look at sodium hydroxide. Sodium hydroxide is a base because as it splits in half, right here down the middle, the free-floating hydroxide ion can begin to catch free-floating hydrogen ions, taking them out of solution and making the solution more alkaline. Negatively charged bicarbonate ion, with that negative charge there, binds really easily to a positively charged hydrogen ion. So of course these are examples of bases because they reduce the number of free-floating hydrogen ions. So of course the body in itself is going to be relatively close to neutral. We said that the pH of blood ranges here, 7.35 to 7.45. And it's going to maintain this normal pH in a number of ways. So first off, when we see acids and bases in the body, they tend to react with one another and form the kinds of solutions that no longer affect pH. So hydrochloric acid, whenever it dissociates, splits right down here down the middle, releasing free-floating hydrogen ions and a negatively charged chloride ion. Then, of course, sodium hydroxide does the same thing. It dissociates into solution, a positively charged sodium ion and a negatively charged hydroxyl ion. So if we begin to look now at how they combine with one another, these free-floating hydrogen ions tend to bind with those negatively charged hydroxyl ions forming water. And water in itself is more or less chemically neutral. And then, of course, we take a look over here at the leftover ions of chloride. And then, of course, sodium. There it is. It's harder to see than I thought. Should not pick yellow. Those two are going to bind together and create a salt of some kind, so sodium chloride. So this is how acids and bases would actually buffer with one another to form the kinds of elements that don't affect pH directly. Now, in addition to that, the body is going to produce actual chemical buffers that resist abrupt and large swings in the pH of body fluids, typically by picking up free-floating hydrogen ions. We're going to see the skeletal system and the digestive system both playing a pretty large role in producing chemical buffers. And then finally, you have the renal and the respiratory, along with the skeletal system, that actually alter their function in order to buffer pH changes. So the renal and the respiratory systems, instead of creating some kind of a buffer chemical, are just going to alter how quickly they eliminate waste. So the renal system with the kidneys can actually create hydroxyl ions or ammonia to buffer as bases. It can eliminate free-floating hydrogen ions more quickly in order to buffer acidity. And the respiratory system can alter acidity by helping you to eliminate carbon dioxide, which, when we look at it later on, works as a transport mechanism for eliminating free-floating hydrogen ions. So the next thing I want you to do is grab your sheet of paper where you've already answered lecture questions 1 and 2 and continue to answer questions 3 through 6. So you'll pause this slide and this video and answer these questions. And then you're going to have one more set of questions to answer, and you're going to take a picture and turn this in via TC Online. So question number 3. Bleach has a pH around 12. What is this considered on the pH scale? So tell me, is this going to be considered an acid or a base? Number 4, glucose has a pH of 7. Let's take it one step further. What does that tell you about the number of hydrogen and hydroxyl ions associated with the solution of glucose? Number 5, cranberry juice breaks down in the blood, and it's going to release more hydrogen ions than hydroxyl ions. And so where is that going to cause cranberry juice to sit on the pH scale? Tell me in terms of a neutral pH. Will it be above or below? Finally, blood in the veins has a pH of about 7.43. What does that tell you about the number of hydrogen and hydroxyl ions that are associated with venous blood? Now, don't tell me they're equal because this is not right at a pH of 7.